Bijou company tonight.
Bijou. Small and intimate.
We may get a few more stragglers coming in, but we need to crack on anyway. So, I don't have any other business at the moment. I do have a couple more of Dave Gavine's very good Dundee Astronomical Society history. If anybody hasn't got one, give me a shout and you can have a copy. Free to all members. And we're also wondering who's all going, if anybody's going to Winchester. Right.
So a different crowd for a change.
Right, small crowd. June and Pam are both good as well. So that'll be at least 5 of us. So we'll organise something around. I haven't booked flights yet, but I'll probably get the 10:30 flight from Edinburgh to Southampton again because that's easy.
It's the best flight to get.
Aye.
Gives you plenty of time.
Aye. And you've time to stop in
Manchester
and get a drink before you go to college.
And sit out there laughing at all the late people coming up the road.
Well, it doesn't open till 3 anyway, so by the time we get in, it's about 3, 4 o'clock before they start doing that.
So, anyway, we'll organise some transport between us and flights and meet up and things like that. So, anyway, the main subject tonight is the mysteries of planetary imaging, which I think a few of us definitely are interested in improving our abilities. And I'll hand over to Alan to explain it all to us. Thank you very much, Alan.
Thank you for that round of applause. Yeah, that's fair enough. Introduction to planetary imaging. I know that some people are interested in planetary imaging, and I've been doing it for quite a few years now. I started off with the old wet film, which was a bit of a disaster, and then moved into the digital age, and it's improved in accessibility for everybody really, with cameras that are available and the free software that's available. But it's one of those subjects that if you just plunge into it and try, there are a lot of mistakes and things you can make. So what I've tried to put together is some theoretical information, which is background information about how the systems work in terms of cameras and telescopes and what have you. And then so I want to do some practical stuff later on. I want to actually show you some video capture. I bought a little video camera here, one of the astronomical ones. The software that I use for that, and also some processing software to produce a final image, which is what I hope to do by the end of the evening. And if there's some time, I've got some stuff on advanced imaging rather than basic stuff, and obviously if you've got any questions I'll try and answer those, so it's probably best to hold them to the end. So what we're going to cover this evening, basic principles of planetary imaging, which are fairly straightforward. Basic equipment, some notes on mounts, telescopes and cameras, quite a bit on cameras because it's quite important. And then I want to look at the capture techniques and the processing software, and as I said, if there's any time at the end, a bit on advanced stuff. So the basic principle for the amateur is what's called lucky imaging. Our atmosphere causes a lot of turbulence and problems when you're trying to look at the planets. It's a bit like trying to look at a pebble on the bottom of a fast-moving stream. It's wobbling around all over the place. So you're going to be lucky to get a clear image of it. And if you want to be lucky and get a good image, you need to take a lot of them, which is why we use video to capture a large number of individual pictures to try and counter the poor seeing, or at least to capture the moments of good seeing that's mixed in with the poor seeing. From those we need to select the sharp subframes or individual images which are half decent and stack them together in free software. What the stacking does is average out the noise that you will get in an individual video frame. When you're looking at a video, I've got some individual frames to show you later, you'll see there's quite a lot of random electronic noise in it. Because it's random, it disappears when you average it out across a large number of frames. So you can start to see the real detail that's in there. So the principles really are lucky imaging and averaging by stacking, and that's how we get a better picture as a final result that's better than any of the individual subframes. Software that I'm going to use, well, I'll talk a bit about Planetary Imaging Preprocessor, PIP, free software, you can download it. And I'll try and show you both AutoStack and Registacks in use if I've got time. I'll talk a bit more about what PIC does for us later. Have to emphasise it, biggest limitation on amateurs trying to get high resolution pictures is our own atmosphere. Two of my pictures, one taken on the 9th of May last year, one taken on the 10th of May, and one's one I would say average scene and the other one's poor scene, and it really determines the amount of detail you can pull out. Some detail as opposed to effectively none. Yeah? So, here's another picture. This is an individual frame taken from a video of Saturn last year when it was at about 18 degrees of elevation. So you can see some of the atmospheric problems in it immediately. You can see atmospheric dispersion effects, the red line across the top, the slight blue line down the bottom. You can see the random electronic noise in the subframe, which is actually cancelling out some of the detail. And also, to me, there's a little bit of atmospheric distortion in there, maybe just the way I'm standing, but that end looks a bit flatter and that end looks a bit more pointed. It's just a bit of the wobble in the atmosphere. Now that's what all of those effects we try and average out with the stacking process. Best piece of equipment that you can have is a good viewing sight with stable atmospheric conditions, but in the UK that's rather difficult to achieve, especially on the east coast here where the prevailing wind's from the west, so it's got all the high ground to tumble over when it comes towards us. Ideally we want a site with smooth laminar airflows extending from the ground to very high altitude. Where are you going to go to get that? No buildings, trees, hills, etc. to disrupt the flow. That's ideally. Most people are going to take pictures from their backyard, so they have to do the best they can. But if you can move to a better site on open parkland, or where, for instance, the wind is blowing off the sea and is nice and laminar, then you are going to get a better result. Thermal equilibrium between the ground and the air above it helps. The time of day can be quite significant. After midnight is very good because the Earth has done most of its radiating of heat away, so the thermal patterns in the lower level tend to have died out a bit. In the higher level there's not much you can do about that. Obviously if you've got a jet stream over the top of you, then you're probably not going to be able to get a very good picture because it's disturbing the air. So the best thing we can do is that, which isn't terribly practical. It sounds nice if you can take your stuff with you. Damien Peach does it twice a year and you look at the results he gets. Yeah. And I would mention that if you look at some of the pictures of planets that you see in the magazines, do look at the details and see where they were taken, because not many of them are taken from a backyard in Fife. Okay. But anyway, so to make the best of it, we'll use a video camera and capture a lot of frames. We'll use software to average out the noise, and then we'll use other software to sharpen it and produce a hopefully interesting and maybe scientifically useful result. So a quick look through equipment. Don't want to bang on about this too much. Mounts, basically two types, alt-azimuth or equatorial. That's a nice Celestron C8, good telescope for planetary work. It's on a alt-azimuth mount. Obviously, alt-azimuth mount has the slight problem over time of field rotation. You can see Cassiopeia turning on its ear there as it goes. Modern software can cope with this over short periods for imaging the planets. If you're taking relatively short videos, it can cope with field rotation. But you are giving the software an extra problem to deal with, so it doesn't always give you the best results. But if that's what you've got, alt-azimuth, do try it, it will work. It's probably easier to use the old equatorial mount, just because there's no field rotation. As long as it's set up properly, it'll follow the planet properly and keep it, as it were, the right way up the whole time. But don't be put off, whichever kind of mount you've got, do use. I get some very good pictures in the SPA from a guy who's got a big Dobsonian telescope. Come on in, come on in.
Happy New Year.
Find a seat.
Oh yeah, Happy New Year.
Excuse me, I'm banging on because I've got a few, quite a lot of information to get through. I get some very good pictures from a guy who's got a big Dobsonian telescope, which is alt-azimuth type, but he puts it on one of these little tilting platforms that tilts at 15 degrees an hour. So effectively it turns it into an equatorial. So, you know, you can get around these things. Try whatever you've got. Choosing the right telescope. Okay, what's the right telescope for planetary imaging? Always the one you can't actually afford. Everybody wants to go for an absolute monster of a telescope for planetary imaging. And there are some advantages to that, but there are disadvantages as well, not the least of which is cost and the number of nights a year when it is a viable proposition to use such a big telescope. So, have a go with the one you already have. If you've got a little 3-inch refractor, you can do planetary imaging. You just can't expect to get large picture scale, high resolution imaging. But you can do perfectly viable planetary imaging. What defines how fine a detail you can see, the resolution, is this little equation, and it's the only equation that's in here. Probably because if there was any others I wouldn't understand them, but the only variables in here are the wavelength of the light being viewed, which we can only affect by using different filters, and the diameter of the telescope objective, and that is by far the biggest impact on how small something you can resolve. By resolution, what I'm talking about is the ability to separate small objects that are close to each other. So on the left-hand side, obviously, if you've got two stars, a very magnified view with the standard sort of airy disk pattern that's formed by either the primary mirror on a Newtonian or the objective lens on a refractor. As they get closer and closer, they start to merge together, and you can only effectively resolve that there's two there when there's a thin black line between them. So when they start talking about resolution in terms of arc seconds, they're talking about the distance between these two centres of the stars. Okay. The reason you couldn't say that's 2 for certain is because on any average night with the visibility bouncing around, it probably looks like that more often than anything else. So the night, the seeing again, is what determines how you can resolve. But there are theoretical limits for the telescopes. On the right hand side I made up some simulations of what you would expect to see. I said under exceptional seeing it's near perfect seeing, almost like viewing through a vacuum, with telescopes of these various sizes as far as the apertures are concerned. This is what you would see at the eyepiece. It's not necessarily what the detail you could pull out after averaging, stacking and processing the pictures. You would expect to do better than this. This is what you would see at the eyepiece. And as you can see, 14-inch, lovely. Not a big drop to 10-inch, and from 10-inch to 8 inches is not much of a drop. So to see any kind of serious detail, optically you're probably looking at 8 inches and upwards. But 6 to 8 inches can produce some very good planetary images, and smaller than that will produce worthwhile stuff as well. So as I said, whatever you've got, give it a go. Briefly about William Rutter Dawes and the Dawes limit. It's just a way of determining what you can resolve with telescopes at different apertures. Just a couple of points on this. The first is that the Dawes limit, and also similar limits like the Rayleigh limit, which does something similar, were derived empirically. This mathematical equation, 4.5 seconds of arc divided by the telescope aperture in inches, is empirical. It's not a natural law. And it was derived using the telescopes he had available to him and the objective lenses he had available to him. And there were pretty few 14-inch objective lenses available to him at that time. And there's quite a lot of research recently which suggests that modern telescopes are busting the Dawes limit regularly. Especially in imaging. But just for information, 3-inch about 1.52 seconds of arc. Is everybody happy with what I mean by a seconds of arc in terms of resolving?
Very small.
Yeah, very small. 1/3600th of a degree is a second of arc, so it's a pretty small piece of sky to look at. Thing to note here is as you go up 3-inch to 4-inch, 4-inch to 6 inches, the changes are quite large. Once you get to 8 inches and bigger, the changes are quite small. Yeah? So there's a thing called the diminishing law of marginal returns. The bigger you make things, you do get more return, but you get less and less and less for each time you look at that. Pictures of Saturn here. Dave Tyler, some of you probably heard of him, he's quite a well-known imager. He took this picture last year when Saturn was at about 17 degrees of elevation from a backyard down south in England with a Celestron C14 telescope. On the same night, at almost the same time, Marc Delcroix took this picture of Saturn from the Pic de Midi Observatory at 9,000 feet up in the Pyrenees, using a 1 metre aperture professional telescope.
What a cheat.
Apart from the fact I hate the guy, because he's got access to a telescope like that, seriously, yeah, it's a better image, but it's not that much better, is it? Yeah, it's not that much. And also, don't forget that this one was taken from the Pyrenees, lower latitude, so the planet was considerably higher up in the sky.
Yes.
So less atmosphere to deal with. So there is a law of diminishing marginal returns. You don't need to go absolutely massive to get reasonable results. You've seen that one before, you'll see that slide again, but I have to keep emphasising it. Quite often if things are going wrong, it's not your fault, it's the atmosphere. If the seeing only allows 1 arcsecond resolution, it won't matter if yours is bigger than mine. Okay. About 8 to 10 inches of aperture, some people say different things, I think Damien Peach says about 10 inches, is what will allow you to resolve just a little bit less than half an arcsecond, which is about the best seeing that you get on in the UK about 90% of the time. So bigger than 10 inches will only be useful to you on about 10% of the nights available in the year, and it has to be clear, you have to be off work, you have to have had everything set up, to catch those. So there is a suggestion that maybe it's not worth spending the money on huge telescopes unless you're going to devote an awful lot of time to planetary imaging. But, I'd do it if I could afford it. There's that thing about Damien Peach, which I've already mentioned effectively. Doesn't stop him going to the Bahamas a lot with his C14. So, just out of interest, I took those simulated pictures. This is a repeat of the slide you've seen before, and I just applied some of the sharpening techniques that I would use on planetary video files to these images, and there is a slight difference. I mean, I don't know that it's a massive difference. I'll just kind of fade back between them again so you can see. But if you look at the 8-inch image in the top right hand corner in particular, I think it improves quite a lot, just with a bit of sharpening technique. So again, another good reason for not necessarily having the hugest telescope unless you want to do this as a lifelong hobby. These were taken by Robin Scargard, who's another SPA member, with a 5-inch Skywatcher refractor, reflector, Newtonian reflector, about a 600mm focal length. Not what you would think of as an ideal planetary telescope. But I think they're perfectly decent pictures for a one-shot colour camera with somebody with no real experience who's gone out and taken these and said, what do you think? And I think he's done a good job. Some fair detail in them. Yeah. That's what I'd kind of buy if I had unlimited funds, but I don't. This guy, R.F. Royce in America, makes fantastic mirror sets of classic Cassegrain telescopes and Dall-Kirkham telescopes. But when you're talking about $10,000 just for the mirror sets, without the rest of the frame that goes with it, I mean, it's a bit Richard Branson territory, isn't it, really? The Takahashi Mulon is an excellent Dall-Kirkham type telescope, but again, they are sky high. You're talking a new car in cost. But anyway.
Euro millions.
Yeah, exactly. It wouldn't stop me if I had the money. Bit about cameras. These are all suitable cameras for planetary imaging. These are all mine. And in fact, that one there is this one here, which I'll try and show you later. A dedicated planetary camera. The ideal camera has to be very sensitive. What we're really looking for is shortest exposures possible to try and freeze the good seeing time. And we want to get as many frames per second captured as possible, so we've got as much data to sort through so that that lucky imaging technique can work. Okay. Ideally, it should have intuitive, easy-to-use capture software that saves in standard file formats. Okay, all of the cameras that you get are likely to come with their own capture software. Some of them save in some funny formats. We can cope with that, but ideally, it would be nice if we could use one set of capture software. And I use Firecapture, which is a freeware you can download, because apart from the digital SLR type cameras, it will allow you to use almost any of the other type of cameras and save in a standard file format, which we can use in other software. But there are other bits of software out there, and the one that you're used to. I like Firecapture because I've been using it for several years over several different cameras, and it's just the same software. So, just to run through them quickly, I started off with modified webcams. Take one of the old Philips webcams, break the case open, and put a nose piece in it, and that would, you know, like get you 15 frames per second or something that you could use, download and process up. Repackaged dedicated webcams. This is a Celestron Next image. Basically, to start with, Mead and Celestron just repackaged Philips webcams, or Logitech webcams, in a nice little case, so they've done all the modifications for you, and gave you some decent software that was a bit more suited to planetary capture. You can pick these up for next to nothing on the second-hand market if you want to get in as an experimentation, 30, 40, 50 quid for the early models, and the new models aren't much over 100, 120. Orion do them, there's a lot of them about, and they're perfectly decent as a way of getting into it. I mentioned digital SLRs and compact system cameras because a lot of people already have them, and a lot of them already have high definition video capture, which you can use. There are a couple of problems with them in that the chip sizes are very big, and 1080p high definition video only is a lot less lines than the chip size usually, so the software in the camera compresses the data, and whenever you compress the data to save it onto the chip in the camera or onto the memory in the camera, you lose some detail. Compressed stuff loses detail. Also, I mean, they're not designed for this sort of work. They've got all sorts of filters in front of the chip which balance the colours towards what we see with our eye, and that's not necessarily helpful. But having said that, they save out in high definition video, which we can load into software. One problem is they do tend to use some odd saving file types. Instead of being like an AVI file, which is the standard for a video, they save in MOV files, .mov, and they all have different proprietary file types for different cameras. But there is that wonderful piece of software called PIP, I mentioned at the beginning, which is Planetary Imaging Preprocessor, which will take just about any file type, movie file type, and do all sorts of wonderful things to it, and then convert it to AVI, which we can use in the other software. So again, use these if you've got them. It's the cheapest option you're likely to get, and you can get decent results.
Is there any advantage in using the DSLR with like repeated taking raw images, stills?
No, because of the number of frames you're going to get in the time scale available. And I'll come on to that. You want as many frames as possible.
Yeah, so you can get better.
Yeah. Probably the best end of the market, if I can put it that way, certainly the end that produces the best results at the moment, are these dedicated industrial or planetary images. Okay, there's a lot of different manufacturers, you've probably seen them in the magazines. You know, Imaging Source with the DMK cameras, ASI and QHY, which are two Chinese manufacturers which make cameras. They're in the price range of about 180 up to about 400 quid, depending on what you get, and they are absolutely ideal for this sort of work. High video stream rates, so we get lots of images. The telescope is acting as the camera's lens, obviously. You can put a digital SLR with its own lens at the eyepiece of a camera, but you're putting a telescope, but you're putting a lot of extra glass in the way. So you're asking a lot of the imaging system to get high quality at very high magnification. So it's better if you use the telescope itself as the lens on those cameras. You can capture to internal memory, more conveniently direct to a computer hard drive. Digital SLRs, that can be a problem for, but there is a piece of software which is paid software you can buy for about $30 from America if you have a Canon digital SLR, which is called Backyard EOS. Some of you may have heard of that. Brilliant piece of software. It allows complete control of the camera over a USB cable. Not only can you then use it for deep sky work with long exposures, but it also has a planetary imaging subsection which allows you to get magnified views of the centre part of the chip and to save them straight to the hard drive on your computer, bypassing a lot of the gubbins in the camera itself, which again means you get more frames per second out of it. So that's useful. I mentioned about capture formats varying. We want to try and get them in AVI file format or sometimes SER format, which is also used by the software I'm going to discuss later. PIP, download it if you like. It doesn't just convert between different software formats. It does all sorts of things. It'll center the target in the frame. That makes the alignment and stacking easier for the later software. It'll crop the frame size down for you automatically, which means the file that gets saved out of it is smaller, so it takes up less room on your hard drive. And it also sorts the individual pictures in quality from best to worst, and you can save them out as the whole lot, like maybe 10,000 if you've done that many in a video, or you can just say, no, just save the best 2,000 for me. Again, which cuts down the file size that you're going to have to deal with later for processing. So a useful piece of software even if you don't use it for digital SLR picture conversions. A little bit of theoretical stuff, moving off the subject of cameras. This is a fairly bog standard PC that I'm giving the presentation on. This is actually the computer that I use to capture my planetary stuff on. I've had it for about just over a year. Picked it up in the second hand, in the January sales in 2016. Didn't cost a lot of money. Most of the software that I know of is written for PCs, not Apple Macs. There is some fantastic picture processing software on Apple Macs, but none of the planetary processing stuff that I know of do run on it. And the other thing is, if you're going to go and sit outside in -5 with frost forming on the end of your nose, it's probably not best to take your £2,000 MacBook Air outside to do that. So, a couple of £100, £300 is a good investment. You can buy second-hand laptops from places like 3000 RPM in Dundee, reconditioned office software laptops for relatively good money. If you're going to do that, I would recommend, if you can, you get one with a USB 3 connection. A lot of the cameras these days are compatible with USB 3 and it can download a lot quicker than the old USB 2 type connections. A few years ago, 15 frames per second over USB 2 was common. With some of the DMK cameras you could push it up to about 60. With this camera here, which is an ASI camera with a USB 3 connection, 150 frames per second is pretty easy. And if I use very small fields of view, I can get over 200 frames per second out of it. So that gives me a whole lot more data to work with. A little bit about cameras. Again, maybe teaching some people how to suck eggs, as it were. But it is important to note a couple of things about one-shot colour versus monochrome cameras. All CCD or CMOS camera sensors start out life as a monochrome sensor. They're just a plain array of picture elements, pixels, into which a photon falls, gets converted to an electron and stored. The sensor has no idea what wavelength of light is falling on it for its colour, none whatsoever. So in order to come up with a colour camera for consumers, somebody came up with a very clever idea, which was a thing called a Bayer matrix, which is this grid of red, green, blue across the front of the monochrome sensor. And each one of those is an individual filter, one filter per pixel element, passing different wavelengths of light. How do you extract a colour picture from that? some clever software has a look at blocks of 4 and averages out the data that's fallen into it to guess at what the colour should be. So if you've got some red pixels have been captured and some blue pixels have been captured but no green ones, you probably take a guess and say it's pinkish. Yeah? The software that does that is called the Debayering Software, and there are lots and lots of debayering algorithms. Some are done within the camera, or you can do it within the capture software. But if you do that, you actually slow down the capture process, because the camera is having to, on the fly, work on each frame that comes off it and debayer it, or the capture software is having to do that as well. So if you're going to use a one-shot colour camera, which is kind of where I'm leading for most people who are starting with planetary imaging, it's much better not to try and capture it as colour data at all. What you want to capture it is raw, monochrome, black and white data. So all you're looking at from each pixel coming off the camera is the number of electrons that are stored in it and their location. And then you can fly data off the chip and store it on your hard drive much faster. Not all capture software lets you do this. Quite often, if you've got a colour camera and you use the capture software that comes with the camera, when you look at the picture, you've got a colour picture. And you've got no way of changing it to a monochrome picture, because either the camera or the software is debayering it. Fire capture, which is one of the reasons why I use it, allows you to capture from a colour camera in RAW. So you get more frames per second, and you can then convert it at a later date, months later if you want, with the stacking software, and change that raw data to a colour picture. AutoStackit, which is one of the stacking softwares I mentioned earlier, does that for you, and it's got one of the best colour debayering algorithms in the business. So why try and capture in colour? Colour files are huge, fill up your hard drive, and they slow down the capture rate. So if you can, capture in RAW, and that's a very useful hint if you're going to do some colour imaging.
Does that mean you can capture it in mono and then convert it to colour image?
If you're talking about using a digital SLR, where you've got a mono mode, it isn't the same thing, because the file that gets saved to the hard drive is a black and white file. You can't convert it later to colour. It's like one of the artifacts that you've added. I've changed it to sepia. You can't change it back to colour.
You use more of a CCD camera though. You know, if in the CCD you've got a choice of monochrome or colour, haven't you?
Not usually. It's usually what defines whether it's a monochrome camera or a colour camera is the presence of a Bayer matrix. If it's got a Bayer matrix, it is a colour camera, but you can save raw data off it in terms of video files and then convert that back later to colour. I'll show you a bit about that, as long as we've got time. I'll show you a bit about that later when I actually look at the practical software we're using. Few things though, because you've got a Bayer matrix in front of the sensors, you must reduce the sensitivity of the sensor slightly, so a colour camera is slightly less sensitive than a monochrome camera. Therefore you have to take slightly longer exposures, therefore you've got more chance of atmospheric effects blurring the image. So monochrome cameras can be sharper for that reason. And the other reason is data in a colour camera, whenever you debayer it, whether you do it off the chip or later on in stacking software, it's still using some kind of averaging process for blocks of 4. So any data that may be significant in one pixel will be averaged out amongst the other 3 pixels. So you do lose some resolution that way. So colour cameras are slightly less sensitive, and they have slightly worse resolution. Yeah.
Would that mean that if you had a monochrome camera, then you'd be able to get some really good shots of like the starry sky, you'll be able to kind of see a lot more detail, and also
You can resolve slightly better. I mean, mathematically, in theory, because you're comparing a block of floor with a single pixel, you can resolve twice as much detail with a monochrome camera than you can with a colour camera. And that's just inherent in the system that's used to extract the colour. Obviously, if you've got a monochrome camera, no Bayer matrix on it, you can still make colour pictures. You do it by taking 3 videos through 3 different coloured filters, red, green and blue, and then combining them.
Like they made the first photographs.
Like we make the first photographs, exactly, through different gel filters. So monochrome cameras are perfectly good for making colour pictures. It's 3 times the amount of work, because you have to take 3 video files. This is a little monochrome camera that I use. It's one of the QHY ones that I mentioned earlier, just to point out that in order to make it work you need a filter wheel and a set of filters. So you've got to factor those into the cost if you're going to go down this route. And for some reason monochrome cameras tend to be slightly more expensive than the colour cameras. Identical cameras, but one's colour, one's monochrome, and the monochrome one's 30 quid more expensive. Not sure why. Different versions of the same chip.
Possibly just the volume in sales that
Possibly,
people want.
possibly right. Yeah, possibly right. What should you buy then? Well, if you've got a digital SLR or a compact system camera, give it a try. They do work. I have used them. One-shot colour cameras are a great place to start. They are much less of a compromise than they used to be, in that the sensitivity seems to go up with every new camera that comes along. This one is the ASI 224MC, the one that's referred to up there, or the colour version of the QHY. They're pretty reasonably priced, I think, for the kind of planetary picture you can get out of them. I mean, you might think 200 to 300 quid is too much to spend, but I think it's a pretty reasonable price for a dedicated camera for that purpose. I don't sell them, I don't get any commission, it's my opinion.
You'd pay that for a decent camera anyway, for like a DSLR.
Exactly.
Yeah.
If you do go to monochrome, don't forget you have to factor in the cost of filters and what have you. The latest ASI camera, the 290mm, which is a monochrome camera, is just amazingly sensitive, especially in the infrared end of the spectrum. It's phenomenal, but it is nearly 400 quid. And then you've got the same again, well, 100 odd on the filters and 100 odd on the filter wheels, and so it adds to the cost. There used to be nonsense about CCD chips being better than CMOS chips. That's all changed in the last couple of years. Most of the best planetary cameras now have got CMOS chips in them, and they work very well. I would say, if you're looking at this, you might get tempted by cooled versions of these cameras that are available on the market. They're not worth it for planetary imaging. I mean, you pay 800 quid for the same camera that the non-cooled version is maybe 250 for. It's great if you want to do long-time exposures of deep sky where cooling the chip's important, but for planetary work, when you're looking at a few thousandths of a second exposure time, it's just not relevant. So don't waste your money unless you're going to take lots of pictures of small planetary nebulas. Right, what do we do now? Capture techniques. Okay. Going to look at general, and then I'm going to look at software specific. Software specific, I'm actually going to use the software itself best I can to try and show you how I do things. General techniques. First of all, patience, and then speed. Why patience? Well, you need to find the bloody thing in the first place. The chips in these cameras are quite small, and it can be very frustrating trying to centre a tiny planet. Even Jupiter, at its brightest, you can put the crosshairs of your viewfinder smack on it, and it can be just off the side of the chip. Go-to telescopes aren't necessarily so fantastically go-to that they'll centre it right on the middle of a tiny chip. So you have to be pragmatic, and I will use a wide field eyepiece, kind of centre it in that, and then a high-powered eyepiece and kind of centre it in that, and then put the camera in, and that works. But finding the thing can be a bit of a problem. You do really need to ensure the telescope is cooled down. A lot of people fall down with planetary imaging by keeping the telescope nice and warm in their study, walk outside into -5 and wonder why the picture is boiling on the camera. It can take hours for a telescope to cool down, especially a big one with a big lump of glass at the back end. So think about, if you know you're going to go out because it looks like it's going to be a good night, think about having your telescope out somewhere in the shade, in a shed maybe, or the garage, where it's going to cool down towards ambient temperature before you use it. Because even a 1 degree difference in temperature between the glass and the air will cause thermal currents inside the telescope, and that will be visible in the pictures. You can see the boiling effects. So cool it down, get an accurate focus. I would really recommend you try and get hold of one of these things, a batten-off mask. I used to have a Hartmann mask, you know, one of those things with 3 holes in it, and you line the holes up when you're focusing. Batten-off masks have taken over since then. You can find them all over the internet for all different aperture telescopes for not a lot of money, or you can make them yourself from plans you can download off the internet. They work by diffraction patterns, and as you move from out of focus through in focus, you end up with this 3-spike pattern, and then out of focus again. And then to get the precise focus, you can see that middle bar there is slightly high, and it's smack in the middle there. And obviously it would be slightly low if you went the other side of focus. So once it's smack in the middle there, then you've got a spot on focus. If I'm doing Jupiter, I'll use one of the little moons of Jupiter, and you put the batten-off mask on that and focus on that, and then swing back to Jupiter. You can focus on a star that's nearby, or you can focus on the moon, and then swing back to your target, but that brings back to point 1 and trying to find the bloody thing again. So a bit of a compromise needed, but the batten-off mask is really good if you've got a point object to focus on. Yes?
Stupid question, because I've never heard of the mask. Where do you put it?
On the front of the aperture of the telescope,
Right.
over the front. Sorry, that's not a stupid question at all. I should have said. It's just a mask that goes at the front of the telescope, and it creates those diffraction patterns that help you focus it. Now you need to wait for moments of good seeing. Back to that slide, can't emphasise it enough, our atmosphere screws things up. But you will, if you sit there, now you're set up and you're focused and you're on the target and the camera's looking at it, you can sit there, and I'd say sit there and have a cup of tea for 10 minutes and watch and see what you've got. And quite a lot of the time you get these jellyfish skies, you know, the side of the planet's boiling in and out or up and down, and there's no visible detail there. And that can last all night, and there's absolutely no point in taking pictures if that's the case. I get lots of guys who send me pictures to the SPA where they've sat out one night and done 40 AVI files and produced 40 pictures, and only maybe one of them's worth looking at. If you sit and wait for a while, and there is going to be some good seeing on that night, you can occasionally see little bursts where the planet stops wobbling, and then it goes on to it again, and then it stops wobbling, and you can see some detail appear, and then it starts wobbling again. If you start to get patches where you can see that kind of detail, just briefly, like the major belts on Jupiter, they appear 2 or 3 times a minute for half a second, 2 or 3 seconds. That is enough for you to start filming, because the software will pick out those 2 or 3 seconds every 10-15 seconds and use those to stack, and you'll get a good image. Yeah? Obviously sometimes you're lucky and you get clear, lots of information every time, but most nights in the UK you have to sit and wait. Times that are useful: pre-dawn skies or the sky around sunset can be very settled. Obviously that's what you need for imaging Venus at the moment, which is why I was a bit short when I was out yesterday when you walked past, trying to I had all my stuff set up. Oh, there you are, sorry. No, talking to the wrong person. A gentleman walked past me while I was set up yesterday, trying to take some pictures of Venus, because the seeing happened to be quite good at the time. After midnight can be good, thermal equilibrium between the ground and the sky. Planetary imaging in mid-spring and mid-autumn, because of this thermal equilibrium thing, can be very, very good after midnight. Not so great in winter when you've got a layer of dense wobbling air on top of us like we have at the moment. The jet stream makes the biggest impact of all. We want ideally to have winds below 30 knots, about 33 miles an hour, 32 miles an hour, at all levels of the atmosphere. The only way you're going to know that is if you start looking on the internet, and there are some good sites that I can point you to if you want to, which will say tonight is a good night to image. Okay, when you've got several of those moments, as I discussed, video capture, and that's when we come back to speed. Why speed? Well, you want to make the most of the good seeing while it lasts. Some planets rotate very rapidly. Jupiter rotates in around 10 hours, Saturn a little bit longer. If you've got an 8-inch telescope resolving to half an arc second and you're looking at the surface of Jupiter with it and filming, a detail of about half an arc second will move significantly enough to blur your images in longer than about 3 to 4 minutes. So you need to take images of less than that length of time. Depends on the aperture, because the aperture gives you the resolving power. One-shot colour cameras, telescope of around 8 inches, yeah, maximum video length 4 minutes on Jupiter. Bigger than that, up to 12 inches, maximum of 3, and if you're Rockefeller or Branson, then 2 minutes is all that you've got available to you. As with a one-shot colour camera, if you've got a monochrome camera, you have to do all 3 of your colours in that same time limit. Yeah? One little trick that you can do is the red frame, just because red light tends to be less dispersed by the atmosphere than green or blue light, usually. The red frame is often the sharpest frame. So if you're going to do this, you can devote most of your 2 or 3 minutes to the red frame and just have maybe 30 seconds each for the blue or the green. Because all they're going to do is provide you with a bit of the colour data, and you can use the red information for the sharpness data. But I'll talk about that at the end. That's called luminance layering. It's a little bit in advanced techniques, but it does allow you to get a bit extra out of it. Saturn, same sort of limits apply, but in practice there's only the fine detail. It tends to be really hard to resolve, except for the biggest amateur instruments. So unless the seeing is exceptional, really you don't need to worry about 2 to 3 minutes. You may even use 5 minutes on Saturn. You'll still get the belts clearly, you'll still get the rings and the Cassini division and what have you. The finest detail will be blurred out, but you're only going to capture that on maybe 2 or 3 nights a year anyway. Venus, Mercury, Mars, no problem with 5-minute video runs, except you're going to overfill the hard drive on your computer. Uranus and Neptune, 20 minutes or more are not uncommon, because there isn't a great deal of atmospheric movement, so you capture as many frames as you like with those. Just a quick word on filters. Everybody knows here, I'm sure, that glass lenses don't bring all frequencies of light to focus at the same point. And even expensive apochromatic telescopes with doublet or triplet lenses that do a bloody good job of bringing light to focus at one point. But when you're talking high magnification work like we are with planets, it's not quite good enough quite often, so you do get some chromatic aberration. Some of the focal points aren't quite perfect. The thing here is, although it can get close enough for our kind of work in the visual spectrum, you've got to factor in the fact that the cameras don't just see the visual light, they can see ultraviolet and they can see into the infrared. And they're not anywhere near brought to focus, even in a £8,000 apochromatic refractor. They're not. So they will soften the image by not being in focus. You'll get blue halos and red halos around sharp points. So what we have to do is use some filters to solve that problem. Anytime there's glass in the optical train, so even if you're using a Newtonian where a mirror does reflect all light to the same point at the same focus, as soon as you bang a Barlow lens in there to get some magnification, you've got the same problem. So we need something like an IR cut filter, a UV IR cut filter. This is an astronomic one on the right hand side. Passes light from just below 400 to just above 700 nanometers, which is effectively the human visual range. Cuts out everything outside that range. Why is that important? Well, as I said, the cameras are sensitive to these light frequencies. This is the one-shot colour camera that's on the stand here, the ASI 224. It leaks infrared horribly. The blue filter you would think would never pass any green or red information. Once you go above 750 nanometers, it leaks horribly and lets infrared light through. So does the green, such that if you're imaging up here at about 850 nanometers, it's effectively a monochrome camera because the Bayer matrix on there just lets all the light through at the same wavelength. So it would be horribly unfocused if you didn't use one of these filters, a UV-IR blocking filter. Yeah? Funnily enough, because it leaks light so much, you can use this with an infrared pass filter and actually film in the infrared as well. But that's a separate slide, I'll show you in a minute. For a mono camera, you need all of your 3 coloured filters, all of which to block the UV and the IR wavelengths. You can't just use a set of red, green and blue optical planetary filters. They're for looking at with your eye. They don't cut out these frequencies, which you need to do. So you need to buy specific filters for this purpose, which again adds to the cost, but they're readily available.
If you apply that filter, can you go back one?
Yeah.
If you apply that filter you're showing us on the right there to that image on your left,
Yeah.
you're going to cut out a lot of your red, aren't you?
I'm
looking at the sort of
it passes to 720 nanometers, so it cuts out
Yeah.
about there,
Yeah,
but that's outside our visual range.
right.
Yeah? That's roughly the human visual range there, from the start of the ultraviolet to the start of the infrared, roughly speaking. Yeah?
Right.
So that particular filter basically just sees what we can see with our eyes. Obviously humans vary slightly, but basically that's what it sees. Yeah, if you use a typical infrared long pass filter which passes from say 600 nanometers upwards and put that on here, you can now see that this camera would see quite a lot of detail into the infrared, and that might be useful as well because sometimes you want to use infrared filters for bad turbulence. When the sky is turbulent, infrared light is a lot less affected by turbulence than visual light. So you could at least get an infrared picture of the planet with some detail on it, even in bad turbulence, just by sticking an infrared filter on the front of this camera. Right, software-specific techniques. Shall we have a quick look at some video capture? That's what I'm going to do anyway. Let's stick a light on for a second so I can see what I'm doing. Thanks. Try and bang through this because it...
Yeah, everybody awake now.
Yeah, sorry if I'm putting people to sleep. Here we go then. This thing's on a tripod just so you can see it. This is obviously not how I would use it. This would normally just go in the eyepiece holder of the telescope. And it plugs into the USB port on here. Hopefully. Yeah. Now then.
Oh, brilliant.
Good. Fire capture. Is my head in the way? No. I can probably just stick the light off again now, thanks. I've just started fire capture, and as you can see, it works for a whole range of different cameras. Including humble webcams down there to support those. ZWO is the particular camera that I'm looking at. I'll just put that over to one side a little bit. Don't do that. Right, okay. There's a live screen here, you can actually see that it's working. I'll play with some settings here. I just want to show you a few things in the capture software. I'm showing you fire capture because I've talked about it and because it supports so many different cameras, therefore it's a useful one to have and it's free. Okay. I'll just turn the gain up, or first of all actually turn the shutter speed up and the gain up, see if I can get some there. Okay, we're in full dark here, but you're still seeing some information off the camera. Right, could we now put the lights on again? I'm sorry to have you jumping up and down. And now I'll take it back down again. One thing you'll notice here is that it's obviously a monochrome camera, except it's not a monochrome camera. If I can come down to settings here, there's a nice little picture of a Bayer matrix down there. I can tell the camera to debayer and capture colour data. Yeah? And now we've got a colour camera. It's not necessarily the right colours. The strobing effect on here is coming off the 50 Hz off the lighting. So you can see that it is in fact a colour camera. But as I explained before, if I capture it as colour data, then the capture software is going to have to look at each frame as it comes off the camera, debayer it, sort it into a package and save it, and that's going to slow down the capture rate and it's going to make the file size very big. I'll just show you in fact that you can change the colour settings. It's currently set for red-green, as in RGGB, red, green, green, blue for the Bayer matrix, but it's got other variations there. You see it's change blue, green, red, and obviously blue, green, so that covers all of the variations. This particular camera is RGGB, so that is the correct colour, although it's pretty miserable. That's because there are no balancing filters in the front of this camera to try and balance it to what the human eye sees. What you're seeing is what the camera sensor sees, and we'll play with the colour data later. So it's a good idea not to capture in colour because it can be confusing. So we'll switch off debayering, and now the camera, all you're seeing off there is the raw data coming off the chip. A couple of things to note. I'm getting 65 frames a second off this at the full size of the camera. But if I wanted to, I could define a region of view like that. Yeah, small region of view. And now I'm getting 300 frames a second off it, just from that small chip. Yeah.
Sure.
When you reduce it like that, is it actually taking part of the chip or is it binning?
It's using part of the chip, because I can use a different part of the chip. It's not binning it. That wasn't the centre of the chip. Just trying to focus you up a bit actually. There you go, slightly better. That was, as I said, it's not binning it at all. So if I just go back to the top and go back to maximum there, see, I could define you over there if I wanted to. Yeah. So I'm using, actually the software is looking at part of the chip. So that's very useful. And 300 odd frames a second I think is pretty good going for what you can get out of these things. Just go back to the maximum field of view. It's really easy to use software. A few things you wouldn't want to use. 16-bit, if you started to save in 16-bit, that's big file sizes again. Don't want to do that. We'll not bother with it. 2 times binning, that gets rid of the resolution of the picture. So we don't want to do that either. So we're not going to bother with that. The various fields of view you can use, I can establish ones, or I can use ones from a drop-down memory of any size I like. 300 by 300 around the middle. Useful software from that point of view. Gain control you've already seen, and there's also exposure control. Yeah. What's the difference between them? Well, the exposure control is the number of the length of the exposure. In this case, it's 1 millisecond, 1,000th of a second. The gain is electronic gain, amplification off the chip. And if you look up in the top left-hand corner up there, if I add a lot of gain, can you see it's adding noise? Noise isn't something to be afraid of. Noise will be averaged out by the stacking software, because you're stacking thousands of frames. The noise is average and it disappears. Don't worry about having some noise, a little bit of noise in your pictures. Use the shortest exposure you can and a sensible amount of gain, such that you can see your target clearly. Yeah? And the shorter exposures will help you capture those moments when the sky is fleetingly steady. The histogram down here is a useful thing. because you can see if it goes all the way to the right like it does at the moment there, you've got overexposure. Some part of the image is fully white, so I'll turn the gain down. It's going to be difficult to get that not fully white because I've got a flickering light tube up there in the corner. But if you're looking at a
Is that
planet,
why we're getting the horrible wobbling on the
flickering
picture?
effect, yeah, it's the strobing.
Flickering light tube,
Yeah, I'm
right.
sorry about that. It's the,
Sorry, so what does the histogram measure? It's
the histogram here. I tell you,
horizontal scale?
the horizontal scale is from black to white
Oh,
in this
sorry, yeah, I
case.
thought it was frequency.
No, I tell you what I'll do just to maybe make it a little bit more obvious. I'll just go back to colour data for you. Yeah, and if you look at the histogram now, you've got red, green, and blue data.
Oh, right, yes.
Right.
It's,
Okay.
yeah, I see.
So it's important to have the histogram probably about 2/3 full to the right, but not more than that, because otherwise you're going to get highlights on the planets which are fully blown out. Yeah, and that looks horrible in a picture. At the same time, you don't want something so dim that you can't see it at all with all the data down here at the left. Right. As far as the rest of it's concerned, it's just things to help you. These are to do with the titling. I've said it's going to go in a folder marked Moon, and it's a red filter, but you've got ultraviolet through to methane, infrared, whatever you want. It's going to be RGB data. You can define all these things, but basically all you're going to do is use that thing there to define a place you're going to save it to, and then you're going to hit save. And as soon as you hit save, it's going to go into that box, and it's going 65 frames a second. I just hit it now. See, it's gone back to monochrome because I've got it set up to do that. I want it to go raw data, which it is, and it's taken 600 frames while I've been talking. Okay, so I'll just stop it because it's filling up my hard drive for no reason. Nearly 1,000 frames. So that's Firecatcher. That's a pretty useful piece of software, and it supports a lot of cameras. Yeah.
You mentioned about noise not being frightened of it. One thing you haven't heard mentioned at all is bias frames, dark frames, anything like that?
For planetary work, generally we don't bother with bias frames and dark frames. Okay, as far as these are technical terms which are useful for deep sky imagery, a dark frame is if you take a 15-minute exposure with a camera of the sky, you get obviously 15 minutes worth of data, but you also get 15 minutes worth of electronic noise, and you get hot pixels in the camera and dead pixels in the camera, just because the chips aren't perfect. Yeah, and that electronic noise can swamp some of the detail. So if you then put the cap on the camera, so you can't, no light's getting to the sensor, and take a 15-minute exposure there, what you've taken is a picture of the noise, yeah, with a dark sensor, so it's called a dark frame. You can then subtract the noise from the picture information, so all you end up with is the data. So that's called dark frame subtraction. That's really a deep sky technique. It isn't really applicable for planetary work.
Same for flats?
Flats, you're not. Flats are a problem. Flat frames are the full width of a sensor is not usually fully illuminated by a telescope. It's bright in the middle and it gets dimmer towards the edges.
So vignetting.
Yeah, vignetting. That's part of the flat frame.
Just show how to pronounce it.
Well, no. So you take a picture of a perfect dull grey screen, yeah, evenly illuminated, and it'll be brighter in the middle and dimmer towards the edges. Now you can then divide your data picture by the flat frame, that picture you've just taken, and it corrects for the fact that it's darker in the corner. It brightens up the corners. Yeah? And also flat frames will get rid of things like dust motes and things that are on your sensor. So, but that's all deep sky stuff. To be honest, it's not applicable for planetary stuff. I've not got long. Right, I've just captured some data. I'm not going to look at that. What I'm going to look at is some planetary data I did earlier. Just show you, this was in the last year. This is a, yeah, thanks. This is a video taken with this camera, and it's a colour camera. This is the raw data of Jupiter, and you can see it's wobbling around in the frame. It's quite good quality because you can see the planet itself isn't wobbling much. It was a nice night, The main detail's visible all the time, and every now and again some of the minor details, like the very thin northern belts, are just popping in and out of the visibility. Yeah? So this is good data. Now this is...
Sorry, is north up for us?
In this case, yeah, north's up here.
Well,
Up there.
up right, yeah.
Yeah, that's the southern hemisphere. The great red spot's not visible, I'm afraid, in this particular one. You might just catch a little glimpse up there every now and again of a little spot appearing and disappearing, and that's one of the moons. But this was 1 minute 26 seconds I took with this camera. I got just over 10,000 frames in that time. Okay? I mentioned PIP earlier on. What I did with PIP was ran the same piece of video through PIP, and what it's done for me is centered it exactly in the field of view, slightly reduced the size of it, and it's selected the best 2,200 frames because that's what I asked it to do, and that's what this video is.
How does it know what we consider a good frame? Does it?
There are lots of different ways of looking at that quality estimation, and it's way above my pay grade in telling you how it's done mathematically. But it's mathematical algorithms that look at the edges, that look at individual details, see how much they're varying, look at Gaussian distributions to see if they can be, or Poisson distributions to see if they can be brought back to a spot. And it would determine whether it thinks it's a good frame or a bad frame.
So basically looking at trying to find the greatest contrast between any 2 points.
Contrast
Which is the
is
same way you do autofocus.
Contrast is one way of doing it. That's called gradient estimation in this software. Yeah, there are different ways of doing it, but that's one of them. Just looking at the edge, looking at pure contrast around the edges is another way of doing it. Okay, so if I look at that piece of PIP video, just because it'll be quicker, I'm going to have a look at auto stacker here. I mentioned this earlier. Unfortunately, the field of view of the screen when it's going through your projector is cutting part of this out. So I'm hoping I can get the whole lot in, but it's a fairly intuitive piece of free software, again, as I mentioned earlier. We'll just open that video up, the PIP one. Yeah. It's appeared over here. Okay, and now look, it's turned it to colour data. It's doing it for us. There's a colour pull down thing up here which is saying force it into RGB. Just like the capture software, if you don't get the right colours, you can change them just by telling it to use something else. Or you can tell it to have a go with auto detect, but it's not always very good. It's got it wrong in this one. So we'll just choose the right one. That's the right colours, that's what we want. Now it's debayering accurately. We're looking at a planet. We're not looking at the surface of the moon or the sun. So we'll use planet. Dynamic background is one of the techniques it uses for centering the planet in the middle of the frame. We've already done that for it, but I'll just leave that selected. Talking about quality estimation, there's edge and gradient here. I'm going to leave it on gradient because edge is something that you would use if you were looking at, say, Saturn or a small planet like Mars, and you can then tailor what part of the edge it looks at. Yeah, so that if you've got Venus sat on its side in a picture, you might have something like that. So it's telling it where to look. But we're looking at whole planets, so we're going to look at the gradients. Local means it looks at quality around the alignment points I'm going to put in it, rather than global, which looks at the whole thing. There's no point of looking at the whole thing because most of it's black. Yeah. So having made those selections, we'll just ask it to analyse it. And it does it really quickly. If you cut it down, 2,200 frames out of 10,000 here, it's done all that and it produces a quality graph with the best frame on the left, the worst frame on the right. Okay. I want to stack some of them, so you can choose the stack format. TIFF is the usual file format I save in. It's a 16-bit file format. PNG is useful for Photoshop if you've got that, you could use that. And FIT, obviously, is a scientific file format in 32-bit. It's absolutely huge. I wouldn't bother with that. So TIFF is what I use. You can just dial in here what the number of frames you want to stack. I've got 2000 set there pre, but you can change that to anything you like. 6, 4000, 1208, whatever you want. Or you can specify it in terms of percentage of the stack quality, 90% or 10%, whatever you want. And you can have up to 4 of each of those, so you could save out 8 different pictures of all different stack sizes. Yeah? And then look at them and see which one is the best. Yeah? I'm just going to save 2000 out of this. As far as this is concerned, normalise the stack. That's only useful if there's variations in brightness. If some thin cloud goes through and it gets dimmer, it just allows for that. And I'm not going to bother sharpening it because I'm going to do that later in other software. It's going to save in the same folder it came from, otherwise you can just specify the folder it came from. Yeah? And finally, you can enlarge it if you want 1.5 times or 3 times, which is useful if the quality is very good. So having got your video here, you've gone through the whole capture thing, I want to define some alignment points on here. You can align them, you can do individual manually drawn ones of any size you like, or you can choose fixed sized ones from the computer, or you can vary those. So I'm going to choose, say, 70, and that gives me a nice comfortable box for it to align features around. So I'm going to run along high contrast features as you were mentioning it, so the gradient estimate has got something to work on. Yeah? And typically, for something like Saturn or Jupiter, I'll use between 20 and 50 alignment points, making sure the whole of the planet is covered. But what I don't do is put any alignment points right on the very edges, because the very edges are the point that tend to wobble most, and they will drag the surface detail with them as they wobble, so they'll blur. What I want to do is align on the surface detail. So there I go, 43 alignment points, that's pretty average. So now all I do is hit stack, and it chunters away in the background. And it really doesn't take very long. It's choosing the best 2000 frames, it's looking at those alignment points, it's lining them all up, stacking them one on top of the other to produce an average image from all of them. And there
How
it's
does
done.
it compare with Registax?
Well, I use AutoStacker because Registax is a bit more complicated to use. That is, AutoStacker is 9 times out of 10 as good as Registax, but it's much easier to use. So that's why I use it. So I've saved that there, yeah. What I'm going to do now, if I can find it, because it was down here somewhere, can you see Registax on here?
It's just here,
There, brilliant, thanks. Registax 6, which is the latest version, which is free, you can use that to stack in exactly the same sort of way. It's just quite a bit more complicated to use. But what Registax 6 has is this fantastic wavelet processing, which once you've stacked a picture, you can sharpen the image quite dramatically with Registax. But I use it because I'll just import the picture that I've just made out of AutoStacker. Yeah, is that the right one? Yeah, there's the 2000 frame folder that was created by AutoStacker when I asked it to save it in the same place. There we go, I'll just open that. Stretch intensity levels, that always comes up, I always say yes, it always gives you a slightly brighter picture. That is the picture that I've just stacked. And you can already see there's quite a lot more detail in there. Yeah, quite a lot more detail in there. Now, there are 2 sides to this program. The left-hand side down here is sharpening, and the right-hand side down here helps with colour effects, to change the colour, to change the brightness and what have you. Talked about the histogram in Firecatcher. You can call up the histogram here, yeah, and all that does is allow you to brighten up the image slightly, like that, yeah, by playing with these sliders. I don't, and then perhaps stretch, and what it's done is just brightened the picture up a little bit, just so we can see what we're doing a bit more. None of this changes the original data. You can always reset it back, and the original data is there, so it's not a problem. You can do what you like with it, and it's non-destructive. So I brightened it up a bit there. The sharpening side here, these are the settings I tend to use myself all the time. Automatic, don't bother with it. Hold wavelet settings, that just means whatever I've determined there, it has exactly the same wavelet settings for every picture I download into it. And I like to try and do things individually. Linear and Gaussian, these are the ones that it comes up with in default, so I'm not going to change those, and they would be there if you were using it. The initial layer is like how violently the sharpening action works. So I'm just going to push that up to 2 and show you by sliding one of these sliders. What these sliders do is look at biggest detail down to finest detail in separate layers and sharpens them individually. So if I just do that, there's quite a lot of sharpening there. Yeah, just by moving that small slide there with level step 2. I personally think that looks a bit unnatural, but it shows you the detail that's in the picture. So I said it was non-destructive, just hit reset wavelets and it's gone. What I do, it's gone back to step 1, and I'll do something which is a bit like the old graphic equalizer that you had on stereos to change the sound. Yeah? But if you look at the picture, you kind of see the detail emerging.
Yeah, gradually.
Gradually emerging. Something like that.
That's brilliant.
Yeah? If it starts to look a bit granular, you've got these denoise up here, denoise. You can plug those up once or twice, and that'll kind of smooth the image out a little bit. A little bit, yeah? Or you can even use the sharpen side if it's not quite sharpened enough for you. You can knock those up or down. But basically, you play with those sliders until you get something you want to see. Yeah?
There's the moon at the top as well.
There, it's popped out. It's just popped out from there. I didn't use that as an alignment point. Normally I would use that as a separate alignment point, but it's just popped out in the data. Just other things on there. I showed you the histogram. The RGB align is useful. I talked about atmospheric dispersion and how you get the red spray at the top and the blue spray at the bottom. If you've not got any correction for atmospheric dispersion, your images won't quite be aligned. Well, you can manually move the red frame and the blue frame up and down with reference to each other, or left and right with reference to each other, just to get them perfectly aligned.
When you're using all these alignment points, is it actually warping each image to match these points?
If I told you exactly how, if I said I knew exactly how it was working, I'd be lying.
Right.
It's
otherwise, theoretically, you only need 2 or possibly 3.
Yeah, theoretically, but it works better with bigger ones. If you had a single alignment point in the centre of the planet, you would think it would work. But it doesn't. The further you move away from the alignment point, the more blurred it gets. It's okay for if you're looking at Uranus, which is tiny, on the chip, you can maybe use a single alignment point. But for big targets like
fuzzy
this,
discs, so the green disc is about the same as a little fuzzy green disc, isn't it?
yeah, but if you've got a big fuzzy disc on your chip, then you've got a very long focal length telescope, and you maybe can use multiple alignment points. If you've got a big thing like Saturn or Jupiter, you want to use multiple alignment points. And as I said, I routinely use between 20 and 50, so 43 in this case, and it's produced pretty reasonable results. If you don't like the colour balance, you can use the histogram up here and change the colour balance. You can see the red and the blue isn't particularly well aligned, and the green is quite badly out. Well, you just say, let's move the green, and we'll just play with the slider until it goes somewhere where I want it. So about there. That's a bit more of a natural colour maybe.
Mm-hmm.
Yeah? Yeah, so we'll just apply that stretch. Okay. Also, there is actually one here which is red, green, blue balance, which has got an auto balance on it, but I find that tends to do some squirrely things unless they're already close to being aligned. So they are now, so I'll just do that. And that's
more like it.
That's,
That's all I'm familiar with.
there you go. So that looks pretty natural to me.
Yeah.
So all I do now is hit do all, which everything that we've done has been reversible up to now. Hit do all, it'll go back to the original image and then apply everything. Bonk. Yeah? And then save image wherever you want it. And that's from that data, captured, stacked, and now there's your picture. I'll just quit out of that. You happy with that?
Brilliant. Yeah.
Right, so we've done some video capture. I don't think I've got an awful lot of time left now. We've kind of looked at the processing software. If I've got 5 minutes, I'll just have a quick look at...
think so.
Yeah, you sure?
Yeah, unless anybody's...
If anybody, you know, I can knock off whenever you like, but just a quick look at some advanced techniques, because I alluded to them. I talked about luminance overlay earlier on when I said you can do most of the data in the red frame and then use that to slide over the top of the colour picture. Yeah, that's because the red frame usually is sharper than the green or the blue. This is most applicable to monochrome imaging through 3 different filters, but you can do it with your one-shot colour. You can use software such as Photoshop to extract the red frame and then lay it as a luminance layer over the top of the colour data. Or you could actually take your red, green, blue colour data and then put an infrared filter on it and take the infrared data and use that as the luminance layer, because in bad seeing that's going to be sharper, so at least you get something out of it. You lay it on the top and you end up with a sharper picture. You might not believe me, but if I put them side by side, you can see that the luminance layer has enhanced some of the detail in the right hand picture. Not dramatic, but it has done it. So if you've ended up with a not particularly brilliant picture, you might be able to enhance it by using the red as luminance.
The great red spot actually looks great and red.
Yeah.
Been getting a bit pilly-willy recently.
It's getting smaller as well. I'll just bang through this and then I'll take some questions. There's not a lot to go. Sometimes the green channel is the one to use because the shorter wavelength obviously has higher resolution, but usually it's dispersed. Ideally, the shortest wavelength would be the blue layer, but usually the blue layer is the one that's least in focus because it's dispersed by the atmosphere. So sometimes they use the green, but mostly it's the red or even infrared in bad seeing. Other frequencies of light, okay. Mono cameras, some one-shot colour cameras such as this one, sensitive in the infrared, so we can take infrared images using other filters. Here is Mars with an infrared pass filter, and you can see the surface detail. Here's Mars in a blue filter, you see the cloud detail. Combine them, you can see both. There's not a lot of point in taking green data on Mars, just because green tends to be an average between the red and blue data. It doesn't do much. So you can save time just by taking red or infrared and blue and combining them. These are some pictures I took on the left of Uranus and Neptune. They're not great pictures. About all you can see is there's some slight colour variation and there's a hint of a little bit of a cloud there. And Neptune, there's really nothing much to see on it, but I picked up some of the moons out there. Much better picture of Neptune over here by Martin Lewis with his big Dobsonian telescope, which I told you about on that tilting platform, using this camera, ASI 224, same camera, with a 610 nanometer long pass filter. That is the filter that I showed you the diagram from. It passes light from 610 nanometers upwards into the infrared. So barely no visible light at all, just a little bit of the red end of the spectrum. And he's got 2 big cloud formations there. Believe it or not, this is a single frame of the raw video that he used to produce this picture. If you've got enough frames, the noise averages out and the data appears.
How many frames was that?
20,000.
They're not huge, you know.
It's not a huge amount. If you consider I got 1,000 frames in the time I made a couple of sentences. Yeah. But 20,000 odd frames in that one. These are the pictures of Venus that I took last night here. And these are ones that took some last year. These are better ones in better seeing. This is an ultraviolet filter on a monochrome camera and an infrared filter. In the infrared it's pretty featureless. In the ultraviolet there's some dark shading. I just make a false colour picture because it tends to emphasise the shading. You can see it much more clearly here. So you can actually track the cloud patterns on Venus. What's interesting actually for this picture more than anything else is the fact that you can see it's not 50% phase, it's less than 50% phase.
Yeah.
Well, this was last night, this was dichotomy, max elongation.
That's right.
It should be exactly 50%.
It's not, is
It's not.
No,
It isn't. Eastern elongations, like last night, they tend to reach 50% phase 2 or 3 days early for some reason. Is it an optical effect? If so, it's not our eyes that are causing it, you can catch it photographically. But anyway, scientifically interesting from that picture. Methane band picture, that is to say it's the absorption band for methane, very useful for seeing new storm features or erupting jet streams in Jupiter and sometimes Saturn. It's a particular filter up around 850 nanometers in the infrared. And here, these are taken minutes apart. I can't remember exactly how far apart they were, 15 minutes apart, something like that. Yeah, 2114 and 2136. You can see this little red fella here is really bright in the methane band, and one of these little disturbances is also bright. They show where storms are erupting quite often before they become visible. So methane imaging is quite useful as well. And that's how the great, what was it called, the Dragon storm on Saturn a few years back, that was found with methane filter before it was ever visual. Atmospheric dispersion correctors. I talked about the way when you're looking at something at low altitude in the atmosphere acts as a prism and splits the light, and that gave you the red band below and the blue band above. Clever little piece of kit. Put it in the optical train just before the camera, and it recombines all the light together. Costs about 120 quid, and it has that kind of effect.
Big difference.
Big difference for low altitude targets. Anything above about 40-45 degrees, you don't need one. But Saturn at the moment is what? It's 6 degrees or something when it's visible in the early morning. It's only going to reach maybe 20 odd degrees at its highest. This apparition this time around. So if looking at something like Saturn and taking pictures, ADCs are invaluable. And I'll just very quickly mention this. Some of you may have heard of WinJupos.
Yeah.
Brilliant piece of software. I've used it a couple of times. It gets around the problem of only having 2 or 3 minutes to film Jupiter before you blur detail. And the way it does it is you take a 2 or 3 minute video, and then you take another one, and then you take another one, as many as you like. You produce the pictures from each of them, put them in WinJupos, and it maps the picture on a globe of Jupiter at an exact timestamp. So you can map half a dozen different pictures onto that globe, and obviously they overlap, and you can then rotate that globe and say, I'll take a picture from that point, and now instead of having one video of maybe 2,000 or 3,000 frames that you've made a picture of, you've got 6 or 7 of them. So you may have 10,000 frames worth, so you can sharpen it that much more. So a cracking piece of software, quite complicated to use, but I mention it here from advanced techniques. It's really advanced processing techniques, and it would take all night to explain that. So really, I hope I've covered everything. I hope I haven't bored people stupidly, and I hope I've given you some information that you can find useful. I'm not sure I have. You did have a question. So.
Yeah, I was just wondering a bit more about exactly what the luminance layer is like. So it's not like more red, is it?
It's not very well explained. I didn't explain it very well. But if you think of shining a light through a church plate glass window, okay, you've got all the colour data there. What you've done is you've taken the red layer, but you're not adding more red in the picture. You're saying that is a plate glass window. Now let's shine colour through
Just
it.
increasing the brightness of all the pixels.
The details, not just the brightness, it's the bright bits and the dark bits. It's the window that you're shining coloured lights through.
Right.
So the window defines what you see, and then you've got the coloured light coming through, which is just giving you the colours of the picture. So the luminance layer is like the window at the front. So you've taken this window and put it on top of your colour picture, and it's a sharper picture than the colour data that is underneath it. In fact, you can blur the colour data that's underneath it a little bit without it changing the quality of the picture that's on top. Because it's the window at the front, the luminance layer, that is actually the picture. So if the sharpest data is in the red channel, you take a monochrome bit of picture of the red and put it down on the colour picture, and now you see more detail.
This reminds me, apropos, absolutely nothing to do with astronomy, but hunting down a lost episode of Doctor Who. The only good quality they had was a monochrome video, because they kept on reusing it. But they had somebody who had recorded it in colour.
Right.
It was a crap recording, it's
Right.
not where recordings were. But they were able to use the crap colour to colorise the monochrome.
Yeah, it's like
version.
shining
It's like
crap
what you
colour
say.
through
It's a
a
luminous
sharp
layer that
monochrome picture.
matters.
Yeah,
It's a luminous layer that matters.
it is.
It's a bit like painting by numbers.
I couldn't tell you. No, I've got an artistic learning
all
body.
the ears stuck to it.
I know it's getting on
Do
late.
that.
Anything else?
You always leaned in it.
Right.
You're talking about the focus and using the mask to
Oh,
focus.
yeah, you're batting off mask.
When you vary the focus, how much are you varying it to make a difference in the?
Well, that depends on the focuser.
Yeah. If you're using a kind of, well, I've got a Moonlight stepper motor focuser.
Right, so it's a twin speed type focuser, is it?
So
Yeah.
how much are you actually changing it to make a difference in the diffraction pattern?
Well, I mean, I can only say, last night when I was set up there using my twin speed Crayford on my Newtonian, you know, you get coarse focus with the outer wheel, it's about right, and then you're making little changes. I mean, it's I don't know, the outer wheel is moving a millimetre or something, and you're looking at the picture on the screen, and you've got the cross on the horizontal line, and the horizontal line is moving up and down, and tiny change, oh, it's moved it down a bit, tiny change, it's moved, now it's in the middle. Now I'm going to lock the focuser and leave it there. So it is very subtle.
It's very subtle.
So a batten-off mask will allow you to get a very good focus.
Better than the eye.
Bit on the eye,
Yeah, better than the eye. Yeah.
Yeah, that's one of the problems I have. That even zooming in the image as much as possible, it's still very hard by eye to get a good focus. So I think something like that mask.
Yeah,
Because I did have a Hartmann mask, but I didn't really see them.
yeah. I mean, I used a Hartmann mask for a while, and the best one I found was the triangular ones, not the round one. You have 3 round holes, and when you're out of focus, you've got 3 pictures, and they kind of move together. And when it's in focus, you've only got 1 picture.
Barnes Wallace's bouncing bomb the lights.
I'll take your word for that.
So is it
You never
better
seen Ghostbusters?
The triangular ones worked because at the points you got a diffraction spikes.
Oh, yeah.
So you got a triangular picture, but you also had spikes out the edges, and it was just a question of making perfect V's off the points. But the batten-off mask is so much better at it.
I presume you could get them from like most Astro.
Yeah, you get them at Rother Valley Optics and 365 Astronomy. If you look at them on the internet, you can find you can say I've got a 6-inch aperture, and there are programs which will print a template, and you can actually draw that on card and cut it out yourself if you want. But they're all over the internet. You can find batten-off
Well, there's
masks.
nothing more complicated than cardboard, though.
It doesn't have to be. I mean, mine one's a plastic one that I bought over the internet for about 15 quid for a 10-inch aperture, and I've got another one which cost me 6 or 7 quid for a 3-inch aperture. Which
Or you could get out of a cornflakes packet.
well, you could do. No, absolutely. That's a good one.
Yeah,
I'm using that with the camera.
So it does, it does the same effect with the camera.
Exactly the same effect with the camera. Those pictures that I showed you earlier on are actually taken
Directly off the camera.
directly off the camera. That was batting off. Where's it gone now?
Click the grey bar in the middle on the left.
The grey bar in the middle on the left. Yeah, thanks. I'm glad you're here.
Can't stand smart ass kids.
I can. Anything that makes the life easier.
You know more about technology than I do.
Well, you
were like that. I think in UK's Mike everybody knows more about technology than you.
These are taken straight off
I got
the
grandchildren covered up next, so.
and you, from grossly out of focus through in focus to grossly out of focus.
Yeah.
And then these are the fine focus adjustments. These are almost in focus, and that's absolutely in focus. With the naked eye, you wouldn't tell the difference between the two. That's why the Batinov mask is so good. And if you're trying to get fine detail on the planets, spot on focus is what you have to have.
Yeah.
Right.
So, are there any other questions for the moment? If not, another round of appreciation. Excellent talk.